will allow you to really appreciate the higher level physics. Some of this stuff gets fairly complicated. But what I want to do is show you the fundamental operational modes of a dielectric waveguide. Then I'm going to show you, based on the mathematics, how you have to do this boundary matching conditions where before when we did rectangular, remember the field components tangent to the walls went to 0. Here with dielectric waveguides, they don't go to 0. They're going to be matched into a mode code in evanescent modes. So anyway, when we talk about dielectric waveguides, before I even start, does anybody have any questions about any of the homework, any of the prior work, any of the quizzes or anything like that? I put the, do you see the solutions on OneNote? I see some people got that for the problems. Do you all see that? The quiz and stuff, and I'll put the one for the homework with the input impedance and stuff. I think I put the other one up there too, didn't I, Jack?
For quiz 1, did you say?
I think I've got all the quizzes up, but if I don't, I do?
Mm-hmm.
Okay, I'll put them up. Anyway, if you have any questions about that, let me know. I'll just mention one thing because, I just want to mention one thing. Again, when you have any waveguide, if you have cutoff frequencies, like FC10 for a rectangular guide's the lowest, then you would have FC20 and possibly FC01 here, and then you'll have FC30 here and such. When you have these, your frequency of operation, if it's greater than this and less than this, only the PE10 mode goes. That's the thing I wanted to stress. Okay, everyone? And that's the way that quiz is set up. That's the way rectangular waveguides 99.9% of the time work. That's my, yeah.
So in that instance where, let's say A is 2 and B is 1, and we multiply B by 2, theoretically, is that equal to FC20?
I think what you're saying is for the problem, we had a dimension A here, and we had a dimension A over 2 here, right?
Yes, sir.
All right, regardless of what A is. In that mode, the fundamental would be found by saying this is going to be the actual cutoff wavelength here by 2, a half wavelength. All right?
Okay.
So you would set this equal to A, right? And then you'd say the cutoff wavelength here is A times 2, right? And then the cutoff wavelength is equal to, well, if you think about it, C over F cutoff, right? If it's air filled. Does everybody understand this? And from that, you can get the cutoff frequency, and this would be for the 1L mode. And you would simply say it's going to be C over 2A. Now for the problem that was given on Friday, if you think about it, C is the speed of light. 2 times an A, I want to say it's 2.2, and I forgot what it is. Is it 8.4 or something like that? 8.6 times 10 to the minus 2. You're going to go ahead and find out that frequency.
6.5.
So that's right, 6.5 gigahertz. You know, the next highest frequency would be the FC20 or the FC01. In this case, it's both of these, and they're 2 times FC10. You all agree with that? What that means is we had an operating frequency for that quiz of F equal to 10 gigahertz, right? Well, 10 gigahertz is greater than 6.56 gigahertz, so we know at least the 1L mode will operate, correct?
Right.
But it's not greater than 13 or 13, whatever it is.
I think it's
Point-
13.
0.06, something like that. So only the 1L mode operates. That was the whole point of the quiz. All the other modes you don't need to worry about. They're not going to propagate. That was the point, right? And from there, you just go through the permutations. I gave you the equation for impedance. I think some people with their calculators made some mistakes where they actually took the tangent and it was meant to be taken in radians, but they took it in degrees by accident. There's operational errors. Get familiar with the calculus. There's a whole lot of tens, though. I want to tell you that. A lot of people made perfect. And the mistakes are not, well, some people didn't know that, but the majority of people knew what they were doing. It was just trivial mistakes with accounting. So that was the purpose of this. Now, back to the dielectric wave, guys, after I did this, try to hopefully answer any questions you had about that one. The dielectric wave, guys, the whole way these things work is just like a rectangular, things bounce off. The difference is that there is a wave that leaks into the other media it's adjacent to it. So let me talk about the slab wave head first. When I talk about a slab wave, guys, it's like this. You're going to have something, a substrate, like this. And this is just one form of a slab wave guy. Then above here, you're going to have some material. And below here, you have some material. Now really, the dimensions out of the board don't mean anything. When you have a slab, you basically have something where you have a dimension here of A, and the thickness here and here of these things you don't care about. They could be infinitely thick for all you care about. This is the critical dimension, the separation. Now, in between a slab wave guide, this will be some epsilon relative, and you can call it of the core. Really, we don't use epsilon relative. They use the intrinsic impedance. I'm sorry, not intrinsic impedance. The index of refraction. This is N, and I'll call it NC here. And it can be called core. Actually, for fiber optic guides, it's called a fiber. Out over here, we're going to have some index of refraction, and you can call this the cladding, but it doesn't matter what the term is. This is going to be a little different from the book. Now, when you have this guide, what actually happens is that the field, simply the electromagnetic energy enters at some angle here, it'll diffract, and then it bounces from here to here, here to here, here to here, and so forth. Get it? That's what goes on. But it bounces at something called the critical angle, or less than the critical angle. I'm going to show you this by blowing this thing up. This is the same, look at this, this is the slab. Here, this I call the core. This is the cladding. And this is the cladding. And I'm going to make some points about this. The separation, or the thickness of this is going to be A. Everything, all the other dimensions don't matter. This has an index of refraction, a core, cladding, right here. And I might say that the index of refraction is square root of epsilon relative in the given material. I mean, not index of refraction. This is called, it is the index of refraction. Now, typically, you get N core will be greater than N cladding. And if I first talk about what happens to the wave itself at the lowest order mode that can propagate, this is it. And it's important you see this. Gosh, I wish I had that. If you get that.
I don't know how it would pull up. I'd put it on here, then I'd put it in there, and it didn't do anything.
Well, you gotta flip the thing to the PC.
And you would put it in the PC.
Yeah, and put it on. Go ahead. Try it. Put it. Here, let me get the screen on for you. I appreciate you doing that. Richard. And you can give it a second, and yeah, you're gonna have to, just see if you can see it. Maybe I have to sign it, but let me just tell you what happens here when we're doing this, while he tries to work on that. If I take a look in this direction of the magnitude of the electric field, right here, then you'd get this. Get rid of that 1 second. Like that. And this itself, from here to here, would be a halfway. It really, if it was a conductor, it would look, that's not really a good drawing, but it would look like this. It would be a half wavelength like this. Remember how a conductor looks? The half wavelength across the dimension that's longest. Here, this dimension out of the board is actually longest. Let me try. But what you'll actually get is not that, but this. You'll get, and this is bleed over. It'll look like a half wavelength, but it'll do this. And what you'll see is the fields here and here. For a rectangular waveguide, they go to 0. For a fiber optic slab, I mean a dielectric slab or a fiber optic pipe, they don't go to 0. And what happens is they die out exponentially in this direction. It's called an evanescent mode. Do you all see that? Now I have to, is that thing plugged in?
Oh, yes. I can also just get it from my email, but,
Where's the drive? It is plugged in?
yes, it is plugged in, but
Go here to start. You should see drives.
can I just go into my email and get?
Yeah, sure. Anything you need to do. While he's doing that, we're just gonna shut that. Oops.
I think it would just be displayed off.
Yeah, but I don't want that thing to shut off.
Oh, then,
Tell you what, I don't care.
yeah.
Go ahead. Anyway, back to this. Here's what really happens. This thing would be a half wavelength if it would short out. Actually, it doesn't short out exactly. It gets small, but it doesn't go to 0. And what happens out here, you're going to get modes propagating in this direction, that direction, that are, they just damp out their evanescent modes. Now, I'll try to explain this in the simplest possible way. When you have a capacitor and you charge it up, right? There's electromagnetic energy around the capacitor, but it's not propagating, correct, class? It's just a static field, right? If you charge up a capacitor, you got a voltage difference. If we had an E-field meter, we could measure an E-field here, but that thing isn't launched. All right? This is called an evanescent field. Here, when we have fiber optics, when we're propagating in that direction, that's the way the wave's bouncing. But there's static energy that gets up here and comes back, up here and comes back, just like a capacitor plate. And the reason it does this is because the solutions to Maxwell's equations dictate that there is some energy here, but it's just like shoved out, comes back in, shoved out, comes back in. And I'm trying to do this in a way that's meaningful. What's the deal? Anything?
I'm getting out what it pulled up.
Now, I said that for a reason. That mathematically, if we solve Maxwell's equations, we'll get field equations that are sine and cosine type of variation in this direction, exponential and that. But we'll also get sine and cosine variations here and here for the field components. And we match the tangent boundary conditions here and here to solve for them. Now, the solutions are what are called transcendental. The only way you can get them is graphically trying to see the intersection of a couple curves. And I don't want to get there with you guys because this is a little advanced. It takes a little time to do, and normally it's done numerically. But it is sufficient to say that with fiber optic guides, the critical feature that determines the minimal frequency they can operate on is this. And I'll talk about it. It's the actual separation of the slabs for a slab waveguide. Y'all follow me on that? And if he pulls this up, I can show you and go through the equations that are in ports. Now that's a slab guide. For a fiber optic guide, where it's circular, is it on?
Yeah, I have it pulled up and now it's turning back on.
Okay, great, great. Well, for a fiber optic guide, the core is round, right? And the difference for a fiber optic round guide in the solutions of Maxwell's equations is, you know how you had sines and cosines in the directions perpendicular to propagation for a conducting rectangular waveguide, right? I mean, you remember that. Well, you don't anymore. For a cylindrical waveguide, the solutions are called Bessel functions. Have you heard of Bessel functions? Bessel functions are solving a differential equation in cylindrical coordinates. All right, and that's the difference. So the radial variation in the electric field will be a Bessel function. I'll show you that, but I don't want to spend a lot of time on it. Because unless you're going to use something over and over again, I don't need to continually count it. I'll give you homework ones. Anyway, here's the thing I was looking for. I think you'll appreciate this, and I'll get to the mathematics and what you would be responsible for. Because if I'm sitting where you are, that's what I want. And I apologize again for this. Is this mouse work? Yeah.
Yes.
This unfortunate process. I want to see if I can get this work. So what I did today, I looked around, and what I wanted to do is give you the best possible picture of what's going on. You've got this slideshow. You don't need to really take notes. All right, but pay attention to this. And I want to give full credit to the author on this one. I didn't create this slideshow, but this thing is fantastic. So let me first give you a little history, and I hope you don't mind me doing this. That guy right there gets a whole lot of credit he won a Nobel Prize, a couple other guys, for developing really all the technology and methods for transporting. I think it was at Stanford when he did this, and you can read about him. And he actually is the one that said we should be getting about 20 dB of attenuation per kilometer. That is incredible. I'll give you a contrast to that. When you talk about copper, all right, coax, for the frequencies we're talking about, we get maybe 200-300 dB, which means the signal's dead. Now, the reason that's important, if you can transmit a signal 20 dB of loss over a kilometer, then about a kilometer away, you get something that catches that signal, it amplifies it, resends it. You keep on doing that, and it means that signal can be sent enormous distance with a few repeaters every kilometer, and that saves a lot of money. So that's important. Let me keep going on. So you can read about this guy. I can only tell you that there's so many people involved in the development, and very few got credit. He's one of them. This is a cool thing. Here's a guy that figured out that, something with a higher order of index of refraction can be used to actually control the light and focus the light, just like a font, just like pipe focuses water. Here's water coming out with a light there, and as it's coming down and dripping, the light's conducting right down that water channel, because the index of refraction for water is much greater, well, not much greater, but it is greater than air. So it bounces and ricochets in there. That's the way it works. And we'll get to the critical angle and stuff like that later. Y'all with me on this? So he noticed it. Then these guys, not just him, this guy right here, and this guy were the guys that came up with the technology. They unlocked the physics, and they're the people that engineered and get a lot of credit for all the development in fiber optic technology that is used today. Remember, it's quartz crystal basically that's pliable and can bend that's being used. Glass, right? Glass has one problem, it breaks. Remember that. If you're ever using around fiber optic cable, it breaks. Anyway, but it's an amazing, and you can transmit orders and orders of magnitude more information on fiber optics than you can a standard coaxial cable. All right. So how does actually information of fiber optic guides, SLAM or just the fiber optic cable work? You all see that digital information off to the left there? You guys are familiar. This would be considered baseband, or this is something with ones and zeros. Here is the pulse, here is the pulse. It's sent. Now, the way they do this kind of thing, there's a lot of different ways to code information. I can say if I get two pulses separated by t, that's a 1. If I get only one pulse separated by distance t, it's a 0. Something like that. That's one method. You all follow me? What you don't get, remember this, unlike AM and FM transmission, You don't get something with fiber optics where you're going to have a carrier here superimposed on that. You don't get something where the amplitude of this thing is actually going to be something that is modulated. The only thing you get is digital packet information. Y'all follow me? This is real important. So they send a burst of information, then it's dead. So if you took a snapshot of time over a fiber optic cable, you would see a whole bunch of photons, then no photons. Whole bunch of photons representing the packets, the ones going down it. So what comes out? Well, there's an optical detector. Do you all know about detectors? You know about photodetectors, right? For the sunlight, you get an output voltage. The higher the intensity of the sunlight, the higher the output voltage, right? Think of that detector. It has to be fast. But now this signal comes in. And remember, it's really an optical signal, so it's very high frequency, but it's bunched over that distance. You with me? It's a packet of photons that are at a certain frequency, and they're coming in, and it hits. Now, here's something. When you have these frequencies and they're coming down a fiber optic guide, theoretically, they would only have one velocity, but the reality is there's some dispersion. Do you remember what a wave with dispersion is? If you sent out a pristine signal, right, in a packet, as it goes, it actually broadens out. It spreads because the velocity distribution, even though it's slack, will cause different frequencies to propagate at slightly different velocities. And the first thing but you should ask is, well, I thought just one frequency propagates. Actually, you can never get just one frequency of photons. When you have individual packets, and this is something I don't think you get in physics. You don't have to have quantum mechanics or higher order physics. But when you create, like when we talk about electromagnetic energy, an E field at a single point in space is made up of what are called photons. That is something at least you've heard, right? A photon in and of itself is the smallest packet of energy that transports information electromagnetically. Now a photon, which is it's hard, don't try to visualize a lot of this, you'll get stuck, and there's all sorts of things you're going to say that are inconsistent. But it does have a polarization, and it occupies a space, and it moves at the speed of light. Follow me? So what does that mean? I'm not exactly sure how to interpret it, but think of it as a packet at a given frequency. That's hard to explain too. It has a given polarization, just accept it. And it's a real packet, it's real energy. And it actually has no, then this is the weird thing, it doesn't have any mass, but it has momentum. Momentum is mass times velocity, so there seems to be an inconsistency. And this is the fun thing about modern physics. There are a lot of seemingly inconsistent things, but they do work, and there's reasons. So anyway, coming out here, you don't get something of nothing and then all, right? All that energy. Part of this is due to what's called the rise time on any kind of photodetector. Y'all realize that all real things that detect changes have a limit to how fast their output can change. Y'all with me? You can't go from no voltage to 10 volts like that instantly. There's a finite time, rise time. There's also something that as this moves through, these would represent packets of light. They'll be broadening here too. So what comes out of a photodetector is something like this, where there's a delta tau right here associated with that. And then there's a space in between them. And I just want to say one thing without getting into too much of this. It can't broaden out too much because you can't distinguish this pulse from this pulse. So that's how come we have to have an actual repeater. Something will take the information, it'll go ahead and bring it down with some signal processing to its original form, then retransmit it. Okay? That's the way this stuff works. If you already know this, I'm glad, but a lot of people don't. So now, here's the way it looks like when we're talking about from chip to chip type of thing. You have a wavelength, you have a divider, different wavelengths. This is for a long haul transmission. You got an optical amplifier. You don't have to know this. This is for your own benefit. Then you're basically going to have the optical signal sent over fiber optic cable. This is a higher order diagram for people that probably have some experience with networking. Have you had networking courses like large area networks or anything like that? Anybody here in Wi-Fi? Okay. Well, if you had this diagram would make a lot of sense to you, but that's just to show you the structure. You can have multi-channels all sending down. Here's the planar flat slab guide I was talking about. Y'all see this? You have basically two different types of materials. An inner one has an index of refraction that's higher, like quartz. The outer one would be basically, think of, well, it could be quartz with less doping or something, but they're very small differences. They're not large differences. So here's what happens in an optical guide. Now, I just want to tell you one thing. When you take a look at this, it's kind of a busy diagram. But here's the thing that I want you to take from it. He's showing that these waves make some penetration here before they actually turn and bounce. In truth, this is called an approximate model by ray tracing. That would work for the ray tracing model. There's a lot more to this. But what does happen, now remember, here that dimension A is for the first mode. Okay, that would be a half wavelength. Second mode would have a full wavelength here. Actually, by the way, the first dimension was a half wavelength here. It's called the O mode. Second mode would have a full wavelength here. Third would have 1.5, and I'm about to show you that. But they're all bouncing at a different angle here, which means they're going at different velocities. And that's bad. That's dispersion. And that's how come here, he's showing you, I put in a pulse of light. This is the intensity. It's supposed to be at a single frequency. And out comes spread. I get spread spectrum versus time when I receive it. He's trying to do a good job of that. But he in fact is. Now, let me show you. What he's really showing you here is some ray tracing where you get constructive and destructive interference. I'm going to forego that for now. This is the boundary condition that you have to have constructive interference. And let me just say this. Without getting into the mathematics, try to appreciate this, okay? I have a signal here. It hits. Consider it to have a phase A, okay? Just think of it. It's got a phase A. Going to hit here. There's a reflection coefficient first along this path length right there, the phase change, right? Then it hits here, it hits a reflection coefficient, then another phase change, comes back here. But when it strikes here, it has to have the same phases as it struck here, call it A, in order to have constructive interference. Do you all follow me? As it gets further and further away from that, there's destructive interference. You follow me? And that wave will not propagate. So what they do is say, if I go from A or from B, or how they start, they say they go from A to B, so it's the lower one to B, and from B to C. All right, these are two distances. It's just from here to here and here to here. That's the total path differences. That minus 2 times the phase change, and this is going to be at the actual surface right here. Oh, wait a second. I'm sorry. Okay, I think you know this. I'm just going to tell you one thing. If I have a wave in general as it's bouncing, it's e to the minus j beta z would be in front of whatever the wave function is as it's bouncing. Are you with me on this? I'm trying to be as simple as possible. So when we take a look at the phase difference, at 0, when z equals 0, the phase here would be 0. At z equals any distance d, the phase change in radians would be beta d. Do you all follow me? That's just the phase change. You go a distance, that's the phase is this, or it could be the cosine argument, right? Think of the inside of the cosine, beta d. Now, if you look here, when he does this, k, by the way, is the same thing as beta. And k itself, you think in terms of, I don't know how he has beta here, but k is really what? Radians per meter, correct, class? Radians per meter, AB, BC, this is the total phase change. Distance times beta would be the total phase change when it goes from here to here to here. But this doesn't include the actual phase effects right there, right? Now, that type of bounce is going to cause a phase change that is added in. He has minus 2 times the phase change. And this has got to be for constructive interference, 2 pi radians times n. Y'all with me on this? Constructive interference, if you take the cosine of 0, that's 1. Cosine of 2 pi is 1. Cosine of 4 pi is 1. Anytime you add 2 pi or subtract 2 pi from the argument of cosine, you get the same value. Y'all follow me in that? So think of this as the argument of the cosine. So now he goes through and says what in fact is AB. Well, AB distance in terms of this distance 2A, he puts the separation at 2A, is simply that distance D or 2A divided by the cosine of theta. And he's got theta here measured as the angle to the normal where the wave strikes the interface between inner dielectric and cladding. All right. Make a long story short, you turn the crank on this, and this is the condition for constructive interference. Now, I want to tell you one thing. You don't have to know this that well. I'm just trying to give you an appreciation. See that M there? That M is the mode number. All right? There's only one. People say, well, why only one? Because the horizontal dimension is infinite. So it doesn't matter. All right? There's only one mode, and it's limited by the separation distance of the two. We could go into the math on that, but you're going to find that that second one could be infinite as far as the separation distance, which means it could actually support a zero-order bounce. Don't worry about that. Okay. And this is generally considered, this is the equation that would have to do with this ray tracing diagram and getting resonant modes, or resonant modes, but don't worry about that. All right, more about beta. I don't want to spend time there. I'll show you what you need to do. This is what I wanted to talk about. Now, this is a perfect picture of the zero mode where you have a half wavelength basically across here, right? Half wavelength right here doesn't go to absolute zero. It's equal to what's called the evanescent mode that's going this way. This mode will die out real quick. So what they do is match the boundary conditions for the tangent electric field there, right? At this point, with this point, and then they go through and get a solution. Now, that's a lot of trouble, but the solutions required, it requires you to do something where you get transcendental solutions, and hopefully I can explain this without scaring you. Here's something, now y'all see what's going on here. Here he shows the zero mode. That's a half wavelength. Do y'all see that? That's the first figure right here. All right. That frequency associated with a half wavelength here to here is the zero mode. That's the lowest order mode that propagates. When you get less and less than that frequency-wise, there's higher attenuation, but it doesn't go to absolute zero. With a rectangular guide, when you go below cutoff, nothing propagates. With these modes, some propagate, but they attenuate very fast. Do y'all follow me? So this frequency of operation, single mode frequency, is dictated by this being a half wavelength. Now the one mode, which would be the 2O mode in a rectangular guide, is right here. Y'all see that? And that's when you get a full wave. And then the 3 mode, or I'm sorry, the 2 mode here, is when you get 3/2 of a wave. But this is a great picture of the way you think about the guide. Now that would be the electric field pattern. If you take a snapshot in time of the photon distribution, you guys freeze time. And it's the thing that's hard to handle because we're sending out packets. It's not a steady state phenomenon like it is in a waveguide. You'll get used to it over time. There's a lot of work in this area still though. This is intermodal dispersion. And I'm going to just mention one thing about this. Anytime you hear the word dispersion, think about velocities of photons not traveling at the same rate. Different mode numbers have different velocities, and therefore they also have something that will cause dispersion. You send a pulse of light that is able to excite more than one mode, you'll get a spreading of the actual spectrum, and that's on the intensity of the output he's trying to show you. He's trying to keep this very basic, and this is a good one. And then he talks about TE versus TM wavelengths. Well, you've had that, right? TE means the electric field is perpendicular to the plane it travels in, or the way I think about TE mainly is say the electric field, when it hits the boundary, is going to be parallel to that boundary. If you take a look at the first one is the TE mode. Yeah, the electric field is perpendicular to the plane of propagation, but when it hits here, y'all see it's parallel to the surface it hits. Y'all follow me? The TM mode, it's the magnetic field that's parallel or sticking out, right? And it hits there, and it's parallel to that. That's the difference between TE and TM. Both can exist at the same time in fiber optics, or for, I should say, slab waveguides. That's called a hybrid mode. You don't have to worry about that. That's beyond the scope of this class. All right, now, all right, I don't want to spend much time on this. See this phi right here? He's getting that from the reflection coefficient, and I don't want to spend time on that. This is what's called a transcendental solution. I'll just say this much. That he's going to get the electric fields inside the core that are tangent, set them equal to the electric fields outside the core at the interface, and you'll see that there's two solutions that are allowed, showed by these line intersections. The black line, I think, is the inner core. It's what he's showing right here. And these are different mode numbers in the allowable modes. It's versus angle. Don't worry about this, but this is transcendental. This is higher up stuff. Normally we do this in the advanced EMAG course. We go through all of this. And when I do things like this on the board, the equations get a little long and more than boring for undergraduates. That's the reason I don't do this here. Now, I'm going to just tell you, they got all sorts of information here about group velocity and all that. I really want to get to is this optical fibers. So, how many have held optical fiber in your hand? See, was yours optical fiber did you held? Was this stuff that's actually used for buried cables, or was the plastic fiber optic used to connect laptop to fiber modes? Or direct?
Both.
Both?
I'm the
Carl?
one wrapped in plastic.
All right, that's very flexible. All right, now if you've got an optical detector, you can plug that into the optical detector, and it's I think the USB or HDMI that plugs into your computer from there, and that can go to like if you've got a fiber optic route system in your workplace or something, you stick that plastic thing into that, and then it's optically connected. It's ultra fast, ridiculously fast. Where did you use that, by the way?
At my co-op.
Second?
At my co-op.
Is your co-op, it's involved fiber optic stuff?
Well, they did like integrated security systems, and so they would use fiber between the different like control panels.
Yeah, investing about fiber for that. If you're involved with cyber or anything like that, it's very, very difficult to do tapping. You can tap a phone line. Anytime you have Wi-Fi stuff, you can use Wireshark and pick up packets. You can do that. You need fiber optic. Anybody messing with that usually has to splice the cable and bang. They know something's wrong. They know somebody's trying to do something. And that's why it's preferred by all the Justice Department in the U.S. unless they've changed. The only way they send encrypted data is with fiber optic backbone. It's a private system. It's off our grid. It's because it's literally impossible to get that information. Not only that, the stuff's buried in the ground, so you gotta dig in there if you want. That's the real reason. But this is a fiber optic cord. Was yours real fiber optic cable, or was it?
Yeah, it was the kind that was buried.
Oh, you actually held a buried one.
Yeah,
About
yeah.
that thick?
hmm
And did you see the cutout of it or not?
Yeah, we were trying to. We accidentally sent it through a wire stripper, and you can't
You
really.
sent a fiber optic cable through a wire strip.
Yeah, you can't do that.
You destroyed it.
Yeah. No, I mean it was like old. It was bad
Oh,
anyways.
you just played them.
Yeah.
And did you actually get into the field of cladding?
Yeah.
It's glass. It's
Mhm.
solid glass. And
It cracks. Yeah.
I've never laid that stuff, but I know about it. I'm looking forward to messing with this because the amount of information you can send is ridiculous. All right, so here's the standard thing. Now, the difference with these things, I want to tell you this much. Here's showing you one mode of fiber optic, the fundamental. Actually, fundamentals is one mode. You show the old one. All right, the solution across here is about a half wavelength. All right, but it's not a cosine variation, it's a Bessel function variation when you solve the del squared equation. I'll just mention this, you're not responsible for this, you don't need to write this down, but I want to at least give you appreciation. This is just a second to give you some kind of perspective. Am I really over it? I'm so sorry. That's on me. What happens is when you solve Maxwell's equation, you get Bessel functions in a radial direction. Last thing, I'm going to let you guys go through this yourself, and I'm so sorry. You see that intensity mapping there? That's how the mode numbers intensity change. For the O1 mode, the 1-1, the 2-1, and the O2 mode, they show you, but I don't want to get into that. And what I'm going to do is apologize to you one more time. I'm going to give you some reading, and I'm going to give you a few problems to do, all right, for Wednesday, and we'll pick it up there. Be safe, and I'll stick around. If you want, we'll do a, without going further into this, any kind of a problem session, consider this my office. If you want to see anything special, I know we don't have the whole class here. Thank you for doing this, by the way, William.
Mhm.
And if you want your grade, come up to me and I'll give it to you